behind it. How do galaxies evolve? There's a number of different ways that I can approach this, but I decided to follow the theme of a pretty good author, I think. His name is Geoffrey Bennett, and he's written a book on the cosmic horizon. And chapter 7, he does call the term, how do galaxies evolve? And there's a nice little question mark there, because up until about 2002, 2003, there wasn't very much in incoming data that gave us an idea about how galaxies evolve. And by that, what I mean is, how do galaxies evolve? You're really borderline between whether you're going to talk about cosmology, which is the science of how the universe came into being, everything that's out there, including time, including space, including how did matter come about. You know, cosmologists, they're a side of astronomy. They're still part of astronomy, but they're more particle physicists, I think. And then you've got astronomers who perhaps look at the mechanics of what we see in the cosmos, how the galaxies behave, and timekeeping, and all that sort of stuff. You know, they're another bunch of people. Can we go to the next slide then? So I'm going to approach it from how this author approaches it. And I'm not telling you, but it is a good book to read. And if you're starting off in astronomy, and bear in mind I don't know where you guys are coming from, you know, what you know of science, but it's a descriptive book of cosmology and astronomy, okay? And it doesn't go into the maths, which there's no reason why you do have to go into the maths in some cases. Before I go on to that, I want to talk about astronomers. Since the 1990s, when I was reading astronomy at the university and graduation, I've looked at what astronomers do after they pass their degrees. Okay, where do they go from there? Now, I had an invitation to go in September to the Yerkes Observatory, which I couldn't take up because of broken bones and things like that inside me. And I would have gone to the Yerkes, and I would have come here and I would talk to you about my 4 nights observing experience in Yerkes. But it didn't come about. And that made me look at astronomy in a different way, and I thought, what are all the other guys who I graduated with? Where are they going? And I'm going to try and talk to you for a couple of minutes. This isn't intended to be in my talk, I've just thought about this now out there. Right? But I've looked at the guys who I graduated with, and some have gone on to be science fiction writers. Some have gone on to become particle physicists, because that's what they want to do. Some have gone on to become astrobiologists. In fact, the professor I studied under, Professor Mark Braith, there was a nice article about him on one of the newspapers, now running a full course degree on astrobiology, extraterrestrial biology, I should say that. And I've noticed that some of the very senior universities in America are now running modules on extraterrestrial biology. Probably because we've now got probes on Mars, and we're beginning to see that things are not quite like the books that we read, certainly in the 1990s. Okay. Give you an example. 3 days ago, I had a message from a pal of mine. He said, do you realize they've now discovered plate tectonics on Mars? In 1993, I can remember writing an essay, differentiate between Earth, Mars and Venus, and on the planet Earth, we had plate tectonics. On Mars, there was no plate tectonics. And that's why we built up the model that you had super huge volcanoes on Mars. But that's changed. The models have changed so much in 10 years. Okay, so if I come here today and say to you, this is the model of how galaxies evolve, I'm not going to stick hard to it. You know, I'm going to be prepared to say 2 years down the road, I'm wrong. And I think you've got to go away with that kind of flexibility in mind. The guys who went away doing science fiction, by the way, are earning good money. We're doing very well selling Doctor Who to the Americans, and they're doing very well selling Stargate and Starship to us. But anyway, so I just fitted that in because In astronomy, you go down whatever route you want to go down. You may want to write books on maths for children to understand. Do it. Because the problems with books today is that people don't understand them. So since I finished university, I'm very lucky. I picked up a sort of job writing on archaeoastronomy, looking around various ancient sites in the Gower Peninsula and recorrecting issues, scientific issues that were wrong in previous books. So I'm on that case until about 31st of January, then I'm on something else. So I may not be using some of the biggest telescopes in the world, but I'm doing what I love doing. But the degree does help you, but you don't have to stick religiously to that subject, astronomy. You can go down different routes of astronomy and satisfy yourself that you're happy in what you're doing. Thank you. I wanted to point that out. Okay. Right. Can you go back? Sorry. Galaxy formation and evolution. How did galaxies evolve from a homogeneous universe? Right. We've got incoming data over the past 2 years. We've got data from the Wilkinson map experiments, or observations, satellite observations. We've got the boomerang experiments. These were balloons going up in the Antarctic, taking images of, or listening to cosmic background radiation. That may sound a very unlikely place, but what happens in the Antarctic if you send a balloon up? And because of the vortices in this particular area, the balloon will actually go around and it'll land back where you sent it up from. So it's a very good way of getting high altitude images of background radiation. You've also got, there was COBE. COBE wasn't a very, it proved that the radiation, the fossilized information of the afterglow of the Big Bang is still there, but the resolution of the images were not something that we could really come to grips with. What we wanted was something where we could analyze the anisotropes in the background radiation. Those are the density effects that you see, or the density ripples that you see in the afterglow of radiation. That's about as far back as what we can go. Can you go to the next one? I think I got it right. Why the problems? What we've got is, that's a very important word, look back time. Telescopes could be described as time machines. When you look through a telescope, you're looking back in time. Now you can go back so many years, millions of years, but there's a big problem. When you go back so far with the telescopes and you're looking to as far back as you can see the first galaxies forming, you've got a big problem. That may be 10 million years, billion years maybe. Well, the GALAX experiments, GALAX is a website that's missions now that are up in space, being run by the Americans. 29th of April, I think the launch date was. They're actually able to detect galaxies 10 billion years ago. So we know that galaxies were there 10 billion years ago. In fact, I saw an image the other day of a galaxy just 1 billion years old. But you've got a problem. And the problem is, in 10 billion years, the universe has expanded a bit more. So the image we've got of the galaxy 10 billion years ago it's changed. That galaxy has changed so much. So the look back time is a problem. Okay? Can we go to the next one? And of course, the other thing I should mention is that in optical telescope time, the further back you go, the light coming towards us is very dim. We don't get a good picture of it. We don't get a good picture of it. Well, you can see that. We know they formed from the Wilkinson map. Wilkinson map observations around about 380,000 years after the Big Bang. Okay. Go to the next slide. first galaxies are probably the quasars. Okay? They're redshifted towards the end of the spectrum to such an extent that we ask the question, how is it possible that quasars can exist? So I'll stand in front of this for a moment now, so it doesn't matter whether you can see it or not. Right, well, what's a quasar? They're the most distant redshift object that we can visibly observe, and it is with difficulty, up until this year anyway. Now they seem to be discovered, I don't know, half a dozen a year seem to be coming out of the textbooks. But a quasar is a galactic system about the size of our solar system. So galaxies are huge, all right? So our solar system, they're an insignificant little bit of light in the middle of well, not in the middle, but 1/3 in of the Milky Way galaxy. So try and picture a galaxy the size of our solar system, and then try and imagine in your minds that you've got a sun 100 times the mass of our sun. It's inside our small little insignificant solar system, and that is producing a huge black hole emitting masses of radiation, converting E into E equals mc squared, and an awful lot of X-ray radiation coming out. That's how we can detect them. In 1990, we thought that these black holes would dissipate out. In fact, I can remember a PhD stating quite simply that these black holes would dissipate out. You couldn't really see that these were galaxies that were the start of what the galaxies that we see closer to us today. I mean closer to us today, I mean closer in time to us today. They're a big hassle, because how do they sort of become a quasar to a spiral galaxy? What's happened in that 13.6 billion years? And bearing in mind that all this was closer together again, mass was much closer together than what it is today, it leads you to the model that small things merge to become big things. Can we go to the next slide? But we needed a guy called Walter Baird to really tell us something about the structure and the metallicity of the stars in galaxies. And what we know about our galaxy and the halo that surrounds our galaxy is that we have galaxies orbiting our galaxy, and we look at the metallicity in the stars of those galaxies, and it's a very interesting point that's become very topical now in university corridors, as I would turn to put it, because I think it was Carl Sagan who says that we are of star stuff. Strictly speaking, we are of galaxy stuff, and what that implies is that we've got metal in our bodies, iron, and we've got lots of heavy elements around us, and we suspect that to trigger off life in the universe, what you need is iron. You don't need gold. Gold is, I'm looking at the ladies here now when I say gold, I'm bound to look in their direction. Gold is formed in supernovas and places like that, but in a sort of natural universe, what you have is all elements will strive to become iron. So you have generations of stars that get born, they go into their novas, they blow up. The iron that they created in their internal structures gets blasted into the universe, that gets knocked on, goes into the formation of another star. So life in the universe really had to take place when star formation had gone through a certain evolutionary track. So the issue of life in the universe has also been linked to life in the universe, because what sort of galaxies do we look at if we're going to suspect life to be there. The halos, the stars in the halos, they give us this little bit of evidence because there's not much iron in these particular stars. And what that's implying is that we don't particularly go to that particular star when the technology does arrive in so many tens of thousands of years. It also tells us that stars in the halos, when they're going around their galaxies, there's a far more random sort of effect. The stars in the disk shape of our galaxy, they're predictable. We can actually predict the orbits they've got around the galaxy, and we can build up certain computational models. And we can also figure out the density waves. The spiral arms, for example, Orion Nebula is in one density arm of the Milky Way, and we can figure out that that will trigger in star formation, okay, because of the density waves. We can go so far also by looking at certain galaxies and looking particularly at how galaxies merge with each other. And we can look at the effects of what's happened after that merger. Now, go on to the next slide, please. Right. Talking about merging, the first working teams, these guys are very, very, very important contribution to astronomy. Okay, the ELS team. Right. If you want to know more about the ELS team, the leader wrote a book, The Extravagant Universe. They made observations of a class, not a class one, as a type 1 supernova, okay, that took place in a very distant galaxy. They took spectrographs of it, and they arrived at some very interesting observations of distant galaxies and mergers of galaxies. They came up with incoming data which corresponded to the boomerang experiments, which corresponded to the Kobe observations, which corresponded to the Wilkinson map observations. If you want an update on the Wilkinson map observations, Sky and Telescope, this edition, I'll by all means come here and have a look at these afterwards if you want to, okay? But the incoming data was perhaps controversial. I'm sure you've heard of a guy called Stephen Hawking. What Stephen Hawking did was he produced a lot of mathematical models, but the one that he's probably going to be controversially known for is the eventuality of our universe coming to a big crunch. I can show it to you later if you're that interested, but we've got a few graphs. I did bring them here, but they're not on this presentation, and that's because I thought I left them in Swansea. But we've got data that says that the universe is expanding, it's going to continue to expand, it's going to become colder, there's not going to be a big crunch. The dark matter and the dark energy the incoming data for this suggests that it played a far more significant role at the time of the Big Bang, but it's not playing a significant role now in galaxy formation. But last April, the Galax missions that's going on now tell us that we're still connected by some kind of metro system to the fossilized afterglow of the Big Bang. Is very controversial. Maybe it's best I don't go down that road. But next slide, please. But these guys, what we've got is a very simple model. Galaxies collapse as single objects out of gas clouds. In the process of gas falling in by gravity, the first halos were formed. As more gas enters, the spin increases and the gas coalesces. Further spinning allowed for greater enrichment of the metals, creating disk inside the galaxies. Okay, that's a very simple model, and it today could be a very simple talk because I've got a lot of confidence in that model. But next slide. As I say, the small to the big path seems to be the observational evidence that we've got. I would think about this a little bit more. The past 9 months I've been working with archaeoastronomers and archaeologists and geologists, and I've been coining some of their words. Uniformitarianism. It means the key to what we want to know today is in the past. I put that in to show a lecture or something, but I wouldn't take it too seriously. But what happened in the past, can we see it happening today in galaxies? When I go on to talk about two particular galaxies that I've been interested in for the past few months, M81 and M82, I am hoping to be able to give you an insight to what those two galaxies have behaved like over the past 26,000 years. And I'd like you to go out and I'd like you to try and look for them, and I'd like you to try and find other galaxies that have experienced similar encounters. Next slide. Okay, I really just put this in for a bit of colour, really. Colliding galaxies, infrared light. But you can see that galaxies do actually collide. Somebody did work it out in a few 2 billion years where we're going to expect Andromeda to come towards us. It's going to be quite an interesting event because we've got two spiral galaxies going into each other. What's going to happen, this is the sort of area I'm involved in, what's going to happen when those two galaxies, will they completely merge as one big galaxy, or will they separate? We have got observational evidence that if you have two galaxies coming in, they collide with each other. They don't really collide, they just interact really. We've got evidence to say that they'll form one big galaxy, but we've also got other evidence that says that what might happen is that one galaxy would probably be a spiral going away, and another galaxy, the remaining galaxy, would be a very irregular shaped galaxy. And we're interested in modeling that irregular galaxy to see if it will one day become a spiral. I suggest at this moment of investigation, I think I'd be predicting that a spiral galaxy with a halo around it, with other galaxies within that neighborhood, is probably an indication of a mature galaxy. And I would suggest that we're not going to find many mature galaxies beyond 10 billion years. Okay, I think anything from 10 billion years to the Big Bang, I think we're going to see lots of irregular things going on. Bearing in mind I haven't seen it yet, but next one, please, Andrew, thank you. The merger model. Proto-galaxies, blobs of gas without stars gravitating together, thus merging to form bigger galaxies. The merger model is still only theory, but the Hubble Deep Field reveals lots of small galaxies, and that would be right. But closer back to the point of creation in the universe we live in, as I mix with a lot of scientists and members of the public who approach me when I'm drinking my local or whatever, I hear stories like, what galaxy are we living in now, what universe are we living in now, what's this 11th dimension universe and all that, and I sometimes think mathematicians are building models that only other mathematicians can understand, so.
You've always done that.
Yeah, it's good fun. I mean, I remember back 1993, I think it was something like that. We had a choice, as students. You're going to have to write some science fiction models, and I didn't want to do it. I said, well, there's forensic science going as an option. Can't we do that? And they said, no, we'd rather you do this. And okay, well, we'll do a little bit more astronomy, and maybe we'll change the course by the time we get around there. And they did actually. They introduced astrospace physics, so I went down that route as well. So, but I do like I was perhaps a bit narrow-minded. I wish I hadn't, because I've been watching this Doctor Who series. The latest one it's really great. I think they're repeating it again. I got to admit, I watched it again, and It's based in Cardiff as well, so it's got to be good, isn't it? Next slide, please. All right, oh yeah, we've got a bit of Wilkinson map data. Right. I really take my hat off to the guy who collected the evidence and took these photographs at the point of creation. I mean, where he put his camera was really marvelous. The quasars are probably around about this point here, okay? I'm interpreting that these blobs of gas, perhaps not even star formation yet, are happening, and we're about there. Okay, and we've got this impression of nice spiral galaxies, or the beginning of spiral galaxies. I'm not really sure of whether we should be assuming that every galaxy that we see that is around about 14.6 billion years old is going to be spiral. And there's observational data that I've made myself through telescopes that do not support this little bit there. Okay, but otherwise, look it up on the internet. WMAP for short, Wilkinson Map observations, analyze their data. I've got it here for you as well. Go on to the next slide, please. I suppose this is another way of looking at it. I would call this a coined word. I studied cosmology under a very popular author. His name was Dr. Patrick Walters. He was a co-author of the standard textbooks that most universities use, The Quantum Universe and Einstein's Mirror. And I actually asked him about this, and going back some years, and he put it to me like this: try to imagine the universe as before the Big Bang. Okay, so it's controversial as to whether we can talk about time, and it's very controversial that we can talk about gravity. But I can remember one day in a lecture, one student got up and said to me, when we discussed the possibility of gravity around about the time of the Big Bang, and he said that he'd never heard anything such absolutely rubbish in his life. And I'm pleased to say that about 3 years ago, in his dissertation on, it was actually the extravagant universe, he did actually say that gravity could possibly be a phenomenon that has to be taken into consideration when one wants to build a computer model for bringing things from the Big Bang up to the present. It's called the Millennium Project. It's run by Durham University. It's discussed in this article here. I'm sure they've got a website, and I think Andrew has got a CD-ROM which does produce the whole shebang from the time of about 1 billion years after the Big Bang up to present-day galaxy formation. And they've got some very good simulations of galaxies merging and forming together, and I'm told that they're going to account for dark matter and dark energy in about 3 to 4 years' time. So I'll be looking forward to that. So perhaps today is a little snapshot of what you might be hearing in the years to come. I hope it is. You know. Next slide, please. Right, good. Now I can talk. Not philosophize. Okay, sorry. I'm sorry. Classically, it's much easier. Right. I've chosen a pretty obvious constellation, the Big Dipper. Okay, and to find the Big Dipper, we go from there straight up about the same distance, and you're going to come up against these two galaxies, M81, M82. What happened 26,000 years ago is that these two galaxies actually collided with each other. If you look at this galaxy here, it's very nice, it's very spiral. If you look at that galaxy there, it's pretty ugly, I suppose, if that's the right word. It's not politically correct, I suppose, but it's not behaving like we expect galaxies to behave. So, what can we understand about this? And before I forget, I know you guys love your telescopes and what have you. We're looking for more models like that. We need a lot more data coming in. So I really would like to give you something practical to do. Okay, please find me more galaxies that have merged and separated. I need to put that into some kind of rational thought. But what we can see is that there's flares coming off there, either end. All right. We know that this one is very active in star formation, and the explanation I think that's best put forward to that is that when a galaxy merges and collides, there's a lot of gas there. There's dark matter surrounding every galaxy, and I'm working on the possibility that when the density waves inside a galaxy get bashed about, and what happens when density waves get bashed about inside a galaxy is that you get star formation. Think of Orion Nebula. You know that these are light years of gas, and I don't like the word gas. I don't like the word particles. I prefer the word smog, but it doesn't sound very good. You can't write smog in a book, but they're very tiny particles in these molecular clouds. And after a galaxy has bashed one of these about, you've got a fair amount of distortion. In fact, I'm wondering if whether the outcome of two galaxies bashing into each other and then separating, and maybe I may be building you a model that makes that there's one galaxy, there's another galaxy, they hit head on, and under those circumstances, I would suspect that they would both stay together gravitationally bound and carry on turning. These two guys, they must have come so close to each other that they became distorted. But interestingly, the biggest one survived and stayed a rather respectful looking spiral galaxy. So I'd like you to go out and find some more for me, please, because we need more data on these sort of events. They're 26,000 light years apart, and 26,000 years ago it happened, and we're pretty sure on that model there. Next slide. Okay, this is just a little bit of data that you might want to go away with. I mean, this is stuff I did about 3 years. The Galax image. Oh, next slide. The Galax mission may have picked this up. Yeah, this is Galax observation. And M81, M82. They're not too difficult galaxies to find. And if you're using the right eyepiece, what you do when you look through a telescope, you can get the two galaxies in the same eyepiece. Okay, so they can be fun to look at, and they can be really fun when you want to talk to people about merging galaxies. And as I say, when you look through the telescope, oh look, there's one and there's the other one. They're both in the same eyepiece, and that makes it a little bit more interesting. And I think it's probably why I chose it as one of my pet observations some time ago. Next slide. I think that's self-explanatory. Next slide. The dates of the first galaxies to have formed is another mystery. I suspect, I don't disagree with this, but I left it. I like the formation of planets in our solar systems. The big devouring the small. It is a bit bullyish, I know, which is not very pleasant, but that happens. Next slide. The end of a formation in a galaxy. Like people and civilizations, stars and galaxies leave behind only artifacts, never evolving the dynamic universe. The ultimate end, I'm not sure whether its end is right, but you know that in every star, hydrogen is fueled to be converted into helium. our star is one day going to run out of its hydrogen. We're about halfway through its life now. Depletion is going to be expected about 4.5 billion years. We'll start burning helium then, and that's not going to be very pleasant because we'll swell up. But I always remember a lecture given at the Open University when the universe will one day lose all its hydrogen, and one by one we're going to see all the stars go up. And I don't know which will end first, the galaxy or the universe. I don't know. It's room for thought, but interesting that this Galaxy mission up there now, and one of the models is that there's some kind of connection, physical connection through dark matter or dark energy between the afterglow of the Big Bang and every galaxy that's out there. I can't fit it together quite in my mind, but you know, this is fun cosmology sort of stuff. Next slide. Oh, this is something about the Galaxy mission, why it's so important. Using the UV area of the spectrum to give us clearer visions of galaxies. It will combine with data coming in from the Hubble Space Telescope. Next slide. I should put some labels on that. We're looking at really galaxies. Some galaxies will form like blob-like, some will be round and some will be spiral. So pointing at Hubble, and give you some advice on this one. Go to the next slide, maybe we got Hubble there. No, I haven't, but yes, we have got Hubble here, 1929. Hubble was, I would say he triggered off the paradigm in scientific revolution when, first of all, galaxies, we discovered that there were galaxies out there. I think it was Immanuel Kant, German philosopher, who said that galaxies were island universes. But when you think about it, 1929, we thought that the Milky Way was the only thing out there. We thought that, there can't be anything else other than the Milky Way. And I suppose when you think about it, it's quite natural for people to think like that, because imagine yourself being a sort of living organism inside your kneecap. How would you describe the outside of your body? This is pretty difficult, isn't it? And, but 1929 to 2005, and we're now so close to getting galaxy evolution sorted out. I think for the next 2 to 3 years, we'll probably have as much data to more or less come forward with a little bit more confidence and say we can now get it sorted. I'm sort of approaching it now in between that incoming data. So, and I think it's important that you go away with making your own models up, okay? And if you want to talk about something that happened on a distant galaxy far, far away and make mega pans out of it, selling it to America or some film industry, go ahead, because other people are doing it. And we owe a lot to Hubble. Hubble points you towards another book. Sir Arthur Eddington, Astronomer Royal at the time around about Hubble came up with the discovery of the Andromeda Galaxy. He produced this book. Okay, he went to his lecture in 1924, and he came back to Britain, wrote this, and this is a second edition hard copy. Another tip for you, okay, this cost me 80 pence in a second-hand shop. We checked up earlier on or last night, it's now worth £47. Okay, so if you want to become booksellers and book buyers, go ahead and do that, but enjoy the subject. Eddington had the job of trying to put this problem of galaxies to the rest of the UK, the rest of Europe for that matter. Behind the scenes, I don't think he liked Hubble very much. He thought of him as an American, which was typical around about that time. Oddly enough, I was reading a book, I bought it down here a year ago, written in 1925, okay? So that's 1929 there, and a book with a foreword in it by the Royal Astronomer, British Royal Astronomer, was saying that there's life on Mars. Mars has a thick atmosphere, clouds. Okay? So just to give you an idea of the resolution of the telescopes around at that time, they weren't very good. So you had lots of things going on. For this guy Hubble to come up and say, hold on, we've got other galaxies out there. It was incredible. Einstein met him, and oddly enough, I think Eddington would have been instrumental in bringing Einstein and Hubble together. And it was a tricky time. You've got the First World War, and then following the First World War we had the Second World War, and of course we had the problem of the atomic bomb. It wouldn't surprise me if Eddington and Einstein, and perhaps a bit of Hubble as well, may have been working very hard on that subject, although I've never read any documents that link all three together. We all know Einstein would have played a part in telling the American government that Germany is in the process of perhaps trying to build an atomic bomb. But three very interesting people all around about that time, 1929. Next slide. Here he is again. Politically correct, smoking his pipe in the telescope. I smoke like a trooper and I have to go outside the telescope where I walk. That's Edwin Hubble. Lots of things are said about him. And lots of things are said also that what has been said about him, we haven't been able to find anything. I think Scientific America have published this something recently about him, the fact that he was a lawyer. They didn't find any evidence that he was a lawyer. The fact that he was a boxer, they didn't find any evidence of the boxer. He was based at the Yerkes Observatory, which I was supposed to go to last month, under the supervision of an astronomer, Dr. Rodri Evans. And there's a funny story about Dr. Rodri Evans. I've got to tell you this. He asked me where I did my observing, and I said, well, this is when he came over from America to Cardiff. And I said, well, I try and go as far west as possible. There's a place down West Wales, you haven't heard of it, Trefarch, but if you hear of a place called Haverford West, you'll find that on the map, but you're not sure if you'll find Trefarch. And he said, I used to live in Haverford West, he said, so it's true that is. And oddly enough, Dr. Rodri Evans was talking to me about Hubble, because he did his PhD in Chicago. And he said, the funny thing is, I hear a lot of people link the Yerkes Observatory with Hubble. That's not the Yerkes Observatory, by the way. But Hubble never, although he graduated in astronomy at Yerkes in Chicago, he never did any cosmology observations with that telescope. It's strange, but it's something that I've noticed in books that get distorted, and you see another edition coming out and that gets distorted even more, and somebody cites somebody else and it gets distorted even more again, and then people of the public read that and just take it in. It's next slide. Bibliography, I think that's probably okay by now. Next slide, if there is one. There might be one. No, I'm sorry. If anybody would like to come and ask me some questions, or would like me to be a little bit more descriptive in, and there's space left around those star-forming areas, so the light will probably appear like something even bigger than supernovas. I've yet to imagine how that's possible. Okay. But
he picked up the pipe when he came to Oxford.
Did he?
He came over to Oxford.
Yeah, yes, that's right. Yeah.
And he picked up the pipe and plus fours and all the sort of habits and apparel of
yeah,
English
that's right, because he
gentleman.
thought that's what you should look like, a gentleman.
And he stuck with it, and he irritated a lot of people back in America because he then tried to speak with an Oxford twang, with an American accent when it is possible.
when the great debates was going on though in America about which would affect